So this is a tutorial about our radiation model. So I'm picking the surface-to-surface radiation model. Now I'm taking the ANSYS tutorial for this one because this is pretty simple. This is a problem of natural convection and radiation. So there is a heated wall. This is a cubic box, 0.5 meter length, and one side of it is at a high temperature. It's filled with air, and we want to see, due to this heated wall, how the temperature distribution is happening inside. Okay, well, at steady state, what would be the condition we would reach? So there are a couple of options we have. We can either use surface radiation model, the U radiation model. There are some other models in the Fluent you'll see. So uh, I will be focusing on the surface to surface model. Now there is two differences, like when do you want to use the discrete ordinate DO radiation model and when do we want to use the surface to surface radiation model. The surface radiation model does not consider um the scattering of radiation because of the medium. Like this is filled with air, okay? But let's say if it was filled with a more viscous fluid which can uh, like scatter the sunlight or the radiative energy by a good margin, which is not negligible, then surface radiation model is not suitable. Then we have to move on to the discrete ordinate radiation model, which considers the scattering of radiative energy uh, by the medium. Okay, by the medium it is filled with air, gas, or some other liquid material, water, whatever it is. Okay, so this is what you need to know before we get into like which radiation model to pick for a problem. So once again, this is important. If the if you know like whatever fluid you're using in the middle of it as a medium, if it has a high refractive index, or like if it can scatter by a good margin the radiative energy, then we should not use the surface to surface radiation model, but we should use the discrete ordinate radiation model. Now, we will not consider solar load for this problem, so it would be pure heat transfer, radiative heat transfer. Okay, no solar radiation, not the radiation coming in from the sunlight or the specular effect or anything. It's just pure a hot body. Uh, we are getting radiative energy from a hot body. Okay. So let's start. This is the geometry. So I already created the geometry. This is the mesh. What I used was just its sizing of this. Number 40, I used a bias and face meshing on all the surfaces for the quadrilateral mesh. So this is my low, like this would be my hot body. I named it as based on the coordinate low x, hot wall, high x is this one, high y, high z, low z is on this side, and low y is at the bottom. Okay, just as the tutorial mentioned, but you can play like do however you want. Okay, so I'll close this one. I'll open again. Okay, so let me close the mesh as well. There you go. I'll start the setup again. Let me just reset it. Okay, so I'll use double precision with a single processor. So a couple of things which is very confusing about like when we set up the radiation model. I'll try to explain those things, focus on those things more. So let's check the mesh. Check it. Okay. Looks good. No negative volume. This would be a steady state. We can apply gravity. Negative 9.81 and model. So we have to turn on our energy equation because this is a temperature related problem. Viscous, there is no high flow rate coming in, so it would be, we can just use laminar flow model. Radiation, so here you see these are all radiation models. So I was just talking about the surface and the discrete ordinate models, mostly for big problems or complicated problems. We use these two, either one of them. I'll not talk about these things. So let's focus on the surface to surface model. So enable this one. If we need solar loading like sunlight or sunlight coming in and heating up the wall, then we need to enable the solar ray tracing. But we're not considering solar load for this problem. Now, while modeling the surface to surface radiation model, uh, 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 this one is, I'll explain maybe a little bit later what this one is, but let's see the settings, view factor and clustering. So this is very important, but very few times we find explanation for this. What is a view factor? So view factor is actually I found a pretty good tutorial on YouTube which explains the view factor quite well. You can go to his channel and see the video. The explanation is about the how the surface model is working, but I'll explain in very brief what you need to know about when you are setting up the model. So view factor is a fraction which determines how much radiative energy will be transferred from one boundary to another boundary. Okay, this is as simple as this. It would be from 0 to 1, and view factor need to be calculated for all the cells. Like from one cell, it would be radiative energy would be scattered all around it, and some fraction would reach this cell, some fraction boundary, some fraction will reach this cell boundary or this cell boundary. Now, how much will cell K boundary will receive? It depends on the view factor. Okay, depends on the fraction. This fraction would be multiplied with heat flux, which would determine how much radiative energy will be transferred or emitted. Okay, so view factor is very, very important. We need to determine that. Now, ANSYS, there are a couple of methods which you can use to calculate the view factor. What ANSYS does is they use a clustering method. Okay, what clustering method is, you can look into the tutorial or the theoretical guide, like how to control the cluster. So mainly it it combines all the faces into one big surface. You can think of it and like faces per surface cluster, you define it. Okay, the more number you have, more number of faces in your surface cluster is, the more accurate it would be, but the more computationally expensive it would be. Okay, so play around with it, figure out a optimum number. Okay, by default it's 1, but you can increase it by, like in this tutorial, Fluent tutorial, they did a comparison of 100, 400, 800, 1600, and showed the radiative heat transfer along the body. Okay, and along the wall as well. So I'll start with 1, and so I hope you understand. And some of the things also I want to show you. So this is how works. What is vfactor is. Now, one other thing is, for example, if there is a boundary at an angle, so it is diffusing the radiative heat along the normal and at an angle. But let's say it is at a side angle. The radiative heat transfer, the radiation cannot um, go across the boundary. Okay, can go across the wall like that. So the view factor of this one, because of the radiative heat transfer from cell J would be 0. Okay, so you can think of it this way, that this wall is not participating in the view factor calculation. Okay, if you have a wall like that, you can the v factor would eventually become 0. So you can let this surface, let these walls or boundaries not participate in the v factor calculation. That would fasten up the process of v factor calculation. And they do that. ANSYS will ask you like, will it be applied to all walls, or even if you go to the wall boundary condition, it would have an option like, will this wall be participating in a v factor calculation? And also sometimes there may be the derivative heat transfer emitted or absorbed on the wall be very small, negligible due to the material properties or some other reasons. So you can also specify that wall as not participating in the v factor calculation. Okay. All right, so that's it. Use the ray tracing and face-to-face. And once we have determined all the walls which should be participating in the wave factor calculation, then you can say compute or read or write. Okay, you have to compute it to create the view factor calculation, and every time you change uh, the wall, if the wall is participating or not in the view factor calculation, you have to recreate the view factor file. Okay, so usually it's better to do like create it after we have specified the boundary conditions. So I'll come back to it later. But if nothing is going to change in the boundary condition, then you could have done it now as well. Let's go to material. I'll not follow the uh, just to save some time. I'll not follow with these material properties and everything. I'll just so the result might not match, but I'll show you the fundamentals. I'll explain the uh, main parts of it. Okay, so I'll just go with the air. You can use an insulator wall or something like that. I'll just mo- modify the aluminum and reduce the thermal conductivity by a lot, so it would be similar to an insulated boundary. Okay, I'm just okay. So fluid is fine, and these are walls. So you can check the operating boundary condition. You can use specified operating density or not. I'm not very sure what this one does, so I'll not explain. And boundary condition is, let's see. So this is high X, which is this surface. This should be insulated as well. So I'll edit one. Now here is another important part, which is very confusing a lot of times, is what kind of thermal conduction should we use? So for the heated wall, we will use the temperature, but for the other parts which would face radiation, we can use radiation thermal boundary or mixed thermal boundary. Okay, mixed and radiation, the difference I think the mainly is you can specify different temperature of air near the wall and at the wall. Okay, so free stream temperature would be your air near the wall, and external radiation temperature would be your wall temperature, you can say. Okay, or you can use pure radiation as well. In the tutorial they used mixed, so I'll just use mixed. What they used was 270 to 93 Kelvin, I think, something like that. And their wall temperature, they use the same temperature, so eventually you could have used the radiation. There was no problem with it. uh, Wall thickness, you can say this is my wall thickness so that it can determine the losses due to the wall thickness. And external emissivity. So now this part, there is sometimes you'll see an external emissivity, there is an internal emissivity. What are those things? And it's very confusing because let me explain through this one actually. So this is the radiative heat transfer equation for the black body, which is purely like an ideal body, like whatever it would absorb, it would emit as well. This is heat flux, not this one. Okay, conduction, radiation is surface phenomena. Not this one. Let's see. Okay, so for the gray bodies, there is an epsilon coming, which is the emissivity of the body. Okay, so the whatever heat would be absorbed for the gray bodies, it would not emit 100% of it. It would emit maybe some fraction of it, maybe 70%, 80%, 90%, based on the material or the surface coating. Okay. So this is gray body. Now, surface to surface model automatically considers, well, actually all the radiation model automatically considers everything as a gray body. So if you want a black body, you can just say emissivity is 1. Okay, so whatever it would absorb, it would emit. Okay, 100% of it. So the way it works is, so this is your absorptivity, this is tau is emissivity, rho is reflectivity. Now, when we assume a surface is opaque, in the transmissivity, like there is no transmission through the surface. So you can think of this figure. So one is whatever is coming in, some fraction, like 100% of the heat flux is coming in, some fraction based on the reflectivity would be reflected, some fraction based on the absorptivity would be absorbed, and some fraction would transmit. Now, if it is an opaque, then transmittivity would go to 0. So the incoming heat flux would, some of them would be absorbed, some of them would be reflected. Now, if it is a black body, whatever is absorbed would be emitted. But if it's a gray body, not everything would be emitted, some fraction of it would be emitted. Okay? So this is what this one is saying. So if it's an opaque body, transmittivity is gone. So it means alpha k plus rho k equals 1. Then due to, according to Kirchhoff's law, absorptivity equals emissivity. He is considering a black body here. So then to simplify the model, to solve the equation, and they're saying rho k is 1 minus epsilon k, and then they use this equation into the radiative heat transfer balance equation to to solve the equation. So you can think of it this way: incoming heat flux. This is at a boundary condition, temperature boundary condition. Some of the heat flux would be emitted, like some portion of the absorbed heat flux would be emitted, and then some portion would be reflected from the total heat flux. So this is the heat in a simple equation, and this is Q out, how much Q is being heat flux is being emitted, and I think I explained this, so I don't need this anymore. Okay, so here's the clearing part. So consider this. Now there is two things happening at the wall. Some of the radiative heat is uh, transferred to the wall, and the wall has its own temperature. Okay, because it has its own temperature, it would radiate some of the heat. Because this is a hot body, it would release some of the it would have radiative heat transfer emitted from the hot body. Okay, because we specified the 293 Kelvin, some of the radiative heat release, heat emitted, would be due to this temperature, and some of the heat would come from the radiative heat transfer from the hot body to this wall. Okay, so there are two things. You can separate them. That would make it easier to understand. Okay, so this external emissivity, whatever this in this thermal tab is, this is due to the temperature of the wall. Okay, so due to this temperature, how much radiative heat transfer, how much emission it would cause. Okay, so you can specify it as 1, you can specify it as 0.9, or whatever. Okay, because this is because of the wall temperature. And Radiation, you can think of it as this is due to the surface coating. Okay, to separate it, to put it very simply, you can think of it as inner surface coating. Okay, because of this surface coating, the incoming radiative heat, some of them would be absorbed and a portion of it would be emitted. Okay, now how much, that would determined by this internal emissivity. Okay, this is very important, and I saw a lot of questions. I had this question as well. So this is the most simplest way to explain this. Think of the thermal tab as due to the material of the wall being hot and radiating, and this is the emissivity for that radiative heat transfer, and this is the incoming heat from some external source. For example, in this case, the hot wall at the low X. Okay, that incoming radiative heat transfer from an external source coming in and heating the inner surface wall, and based on the surface coating, how much it would emit, how much it would reflect. Okay, this is that emissivity. Okay, whatever the internal emissivity is, 1 minus that value is our reflectivity. Okay, reflectivity of the inner wall surface. Okay, so we can specify maybe 0.9 is our internal emissivity. Okay, and then the other portion would be our reflectivity. Okay. Okay, so because there is no transmissivity in here, and this emission for the surface to surface model would always be 100% diffused. Okay, it would not depend on the incident angle. It would just diffuse in all direction. I know that this is important as well. Now it's asking me if this wall is going to participate in the view factor calculation. I should enable it because this would be very important. How much radiative heat transfer is coming in? There is significant radiative heat transfer in this wall due to the incoming radiation and hitting the wall, so it should participate in view factor calculation. So I should enable this, click apply, and I think all the other walls would be similar boundary conditions. So what I would do is I would just copy this boundary condition to the other walls, not the hot walls, because that would have a different boundary condition. Okay, so they have been copied. I can check it in here. Yes, they have fixed. You can change. Yeah, I only have aluminum, so but you can just create another. Like in the tutorial, they created an insulated insulation material, so you could have done that. And the hot wall temperature. So what I would do is in the thermal, I'd specify a temperature boundary condition. This would be a source for the other walls, external source for the other walls. Let's say this is 470. Okay. Wall thickness doesn't matter actually because this is the hot source. So other radiation energy coming in and being reflected, that would be negligible. So I'd go with this one, and radiation, this would participate. Again, even if this one doesn't participate, I think it would not matter because other, let me think. No, this would matter. So it has to participate in the view factor calculation. Okay, internal emissivity is 1. Everything is being emitted. Click apply. Phases per surface cluster. Again, you can increase this one to have a better accuracy of the radiative heat transfer from this wall. Okay, for now this is 1. By default it's 1 for the simplicity of calculation. Now we are done with the boundary condition. We can go back to the radiative heat transfer and compute. I already created one, but usually with the first time you should not see anything in here. File name, you can name it differently. You can even have multiple ones, and like first time you create that, then later on if you want to change it, you can create the new one or read. If you already have created one, you can just read the existing vfactor file. Okay, what it did was it calculated all the f values, So let me show you how it should look like in a matrix form. So basically we are solving this equation. You see it's multiplied with the heat flux, and this F1 to F1 3 F2 3 based on the number of elements, it will calculate all these F values, okay, and create this stiffness matrix. Okay, this J is called radioactivity vector. Anyways, other than that, let's see, boundary condition was the confusing part. Methods, you can go with the default for the other features. I'll skip those things. One thing they did in the tutorial is they play with the relaxation factor because this the air is trapped inside and there is a hot side of it. Air keeps recirculating, so it's difficult to get a steady state. So what they did was they reduced the momentum relaxation factor to 0.1. You can play with it, okay? That would stabilize, but again, the accuracy can go off, so be careful when you change these values. If you don't know, don't understand it, don't change anything in here. Okay, initialize, again, initialization was done, no inlet and outlets, so you don't see those numbers usually pops up. And I would run for 1000. I think it would not converge, but it should stabilize. I'll come back after. Okay, surprisingly, I used a different boundary condition last time, and the material properties and everything, but surprisingly, it converts really fast. Let's take a look at the results. Let's take a look at the temperature at the wall. Okay, so this is how it looks like from the hot body. Temperature is being distributed, looks reasonable and quite well. Okay, you can see at the corners, I think you can think of it this way is these are the corners, so fewer radiative heat transfer from this hot body would reach the corners compared to the middle. So the middle part is a little bit higher temperature. Okay, and this is how it looks like. This is completely hot body, high temperature. Let's create a surface in the middle, plane in the middle. Yeah, let's take a look at how this one looks like. Maybe I'll create an XY plane as well. Okay. So I really should restrict this one, maybe 423. I don't know. It's gone. 450. Okay, not high enough. 465. 470. What happened? Okay, I think the temperature is this. This is the problem. Okay, let's do 300, and let's do this 350 maybe. This is strange. Yeah, I just need to play with this one. I just randomly put the boundary condition, so uh, maybe I don't know, 320. I will start seeing the difference, but the point is you can always take a look at the wall temperature. Okay. Oh, okay. So this is why it was not showing. Sorry about that. And that's not a wall, so the static temperature. My bad. Uh, Forget about this one. Auto range. Okay, so this is the temperature distribution. Plane 6, plane 7. This is how it looks like. This is how the temperature is being distributed from the hot wall to the other walls, and that's it. Okay, so this is how you can set up the do a purely surface radiation model. Again, the important point is you should only use the surface radiation model when the medium, like in our case, it was air. It is not uh, scattering the radiative heat transfer by a lot. Okay, if it is at some significant difference, like it can change the incident radiation, which would change the result of the actual scenario you want. Okay, so make sure it is like that. If you are using like sunlight is passing through the air, not much of it actually changes the angle. But if it's too dusty or too thick, like if it passes through water, it does scatter a little bit. And if it is significant in your problem, you should not use the surface-to-surface radiation model. Instead, you should use the discrete ordinate radiation model. Okay. So this is how you can do the surface radiation model. Thank you. And one other thing is uh, be careful about when you specify the emissivity. There are two types of emissivity. One is due to the hot wall body. Another one is due to the surface coating. Okay, the incoming radiative heat emissivity. So specify those carefully and specify the view factor. And if you want to change the view factor, what you can do is I would recommend once you have done this, you should go to the model, go to radiation surface, go to settings, and increase this one maybe uh, 1000. Okay, 1000. 1000 phases per cluster. You'll see it would take quite a big time, so maybe this is 1000. Let's name something and computing it. So it has created a new one. Click OK, and then maybe one was good for your problem, but like for example, this is a pretty simple problem, so I think one was good enough. But a lot of cases you need more accuracy, so you can initialize and run calculate for that one with a new view factor calculated based on the parameters you have set, and then compare the results and make sure your simulation is showing you an accurate result. All right, I'll stop in here. Thank you very much.